First, in the klystron power supply, we are going to give the supply. So on the klystron source, it is going to generate the oscillations, or we can call that as the microwave signals are generated. And isolator, it will allow the signals in only in one direction. And variable attenuator, in order to maintain the attenuation level. And the frequency meter is used to measure the dip frequencies. And the slotted line carriage is used to measure the wavelength, or we can call that as VSWR, by taking the Vmax as well as the V minimum. So and here we are going to connect the last one, unknown load. Unknown load is nothing but actually the detector mount. Okay, so or we can call that as the crystal detector. So in the detector mount, so once we take the readings from the detector mount, so then we are going to remove that, and we are going to connect it to the movable shot, and we are going to take the V minimum, first V minimum as well as the second V minimum, and we'll observe the output on the CRO. So let's start with the conduction of the experiment. We have arranged the experimental setup, and we have connected the detector mount, that is nothing but the unknown load. So and we have generated the mode and the SLC in the right extreme corner. So here first what we have to do is, so we need to move this slotted line carriage, so to get the maximum voltage. So here we need to measure the maximum voltage. So here we can observe the maximum voltage is 872 millivolts. So next, and we need to measure the minimum voltage. So along with this minimum voltage, here we are getting the minimum voltage. So here we should take the minimum voltage, that is 512 millivolts, and we need to measure the distance. So here in order to measure the distance, there will be a vernier scale on the slotted line carriage, and here the one more scale. So the line 0 coincide with the vernier scale, we have to take that reading. So in this case, the 0 is coincide with the value of 9.8, nearly 9.8. Okay, so x1 value is 9.8. So again we need to take the, okay, next we are replacing the detector with the movable shot. So here we need to consider the V minimum as well as the x2 as well as x3. Okay, x1, x2 is actually the distances. V minimum 1 distance, V minimum 2 distance. So first we need to move the slotted line carriage. So this is actually the V minimum. V minimum 1. So V minimum 1 is actually 100 millivolts, and we need to find out the distance. Here the distance is exactly 9. Okay, 9 centimeter. And next we need to take the second V minimum. So this is the second V minimum. So second V minimum is the peak to peak voltage is 140 millivolt, and the distance is nearly 11.1. Okay, that is x2 as well as x3. So once we tabulate the readings, we need to calculate. So here we have taken the V minimum as well as V maximum, and that is the, for V maximum, whatever the distance we have taken, that is x1, that is with respect to the match termination, or we can call that as the unknown load. And when once we replace the unknown load with the movable shot, we need to take the first V minimum, the voltage as well as the distance, that is x2, that is 8.9 centimeter, and the V minimum is equal to 56 millivolts, and x3 is equal to 11.4 centimeter. Okay, so and in order to calculate D, so that is actually the, okay, the D is actually the distance between the first minima as well as the second minima, that is equal to x3 minus x2. So according to these readings, D is equal to 11.4 minus 8.9, will get D is equal to 2.4 centimeter. And in order to find out the lambda G, that is the wavelength of the waveguide, that is equal to 2D, and lambda G is equal to 2 into 2.5 centimeter, then lambda G will get 5 centimeter. and in order to find out the delta L, that is equal to x2 minus x1, that is equal to 8.9 centimeter minus 9.6 centimeter, will get 0.7 centimeter. Even though if we get minus, if we take the magnitude, then we'll get, that is actually the positive value, 0.7 centimeter. And lambda c is equal to 2a. A is nothing but the width of this waveguide, that is equal to 2.3 centimeter. Okay, so then we'll substitute that value. Lambda c is equal to 2 into 2.3 centimeter. Then we'll get lambda c is 4.6 centimeter, and we need to find out that lambda naught, that is equal to lambda g into lambda c divided by square root of lambda g square plus lambda c square. So once we find out that, lambda naught will be getting that as 0.033, and in order to find out the impedance, this is actually the formula. Z naught is equal to 377 divided by square root of 1 minus lambda a divided by lambda c whole square. Okay, so then we'll substitute this value and we'll get the Z naught is equal to 541.145. Okay, and in order to find out the impedance on the Smith chart, so we need to find out the VSWR. So VSWR is equal to Vmax by V minimum, that is nothing but 2.24 divided by 1.01, will get 2.01. VSWR is 2.01. Okay, and lambda L by lambda G is equal to 0.7 centimeter divided by 4 centimeter, that is equal to 0.14. Okay, in order to find out the impedance, so we are going to make use of the Smith chart. So this is actually the Smith chart. I think you people studied the Smith chart. So first we need to take the VSWR. VSWR value is 2.01, or we can take nearly 2. So 2 is actually the radius of the VSWR circle. So here we need to take 2 as the radius, and we should draw the circle. So this is actually the VSWR circle, and here this end will consider that as the open circuit. That is equal to, so this end is actually represents the open circuit, and here we'll consider actually the short circuit. So, and the whatever the value will get that as lambda L by lambda G is equal to 0.14. From the short circuit end towards the load, we should take 0.14. So here you can observe. So this is the second line. So from 0, 0, 0.01, 0.02, 03, 04, 05, 06, 07, 08, 09, 0.1, 0.11, 12, 13, 14. So this is actually the point with respect to the lambda L by delta L by lambda G. Okay, so once we get this point, so we need to join from O to the lambda L by delta L by lambda G point. So this is actually the intersection point. So in this intersection point, we are going to find out the impedance. So in order to find out this impedance, we should take the VSWR circle where exactly it will cut. Impedance means R circle as well as the J circle we need to see. Okay, so here this is exactly the value of So from this point we are going to find out the impedance. So R circle cuts the value of 0.9 and the J circle is actually 0.65. So and here we are taking at the downward, so we should put it as a minus. So the impedance will be considered as Z0 is equal to 0.9 minus J 0.65. So this is the impedance value we are going to get. So whatever the value we are taking from the Smith chart, that is actually the normalized impedance. So this is the impedance of the load, or we can call that as the load impedance. So once we get the normalized load impedance, that has to be multiplied with the Z0. Okay. So 0.9 minus J 0.64 or 65 into Z0. So Z0 is actually, we have calculated as 541.145. So when we multiplied that, so we'll get the load impedance as 487 minus J 355. Okay, 355 ohms. This is actually the load impedance we are going to find out from this experiment.
VSWR is defined as the ratio between maximum voltage to minimum voltage along a transmission line, is called VSWR. To perform this experiment, we will use slide screw tuners, SS tuner. We can see here, it will slide left and right direction. A pin is penetrating in waveguide. Penetration of pin is depend upon plunger placed at top of it. When screw is completely open, there is negligible reflection will occur in waveguide. Reflection in waveguide will increase as increasing depth of pin into waveguide. We connect SS tuner after slotted line section. Match termination is connected at end of microwave test bench. Now we connect tunable probe to DSO with help of a BNC cable. Power on DSO and keep amplitude and time base setting as shown in video. Ensure that initial position of variable attenuator is fully open. Now power on klystron power supply and proceed with amplitude modulation for getting square wave at output on DSO. If you don't know how to get square wave at output, you can refer lab manual or previous video of this channel by clicking on I button. Adjust tunable probe for getting a good amount of output. Now, we will perform low VSWR measurement procedure. For measuring low VSWR, sliding screw tuner must be set at completely open position. By using slotted line section and tunable probe, you can measure amplitude of minima and maxima. Note down amplitude values of maxima and minima. Here, position where we are getting minimum possible amplitude by moving slotted line section and tunable probe as known as minima. Here we got minima. Note done amplitude of minima at this point. After getting minima, we will go for a maxima position. Move tunable probe along with slotted line section and get a value of maxima. Here, position where we are getting maximum possible amplitude by moving slotted line section and tunable probe as known as maxima. Here we got maxima. Note done amplitude value of maxima at this point. In calculation, you can easily find out value of VSWR and reflection coefficient. Thank you.